When we talk about the evolution of artificial intelligence, one of the most important transitions happening right now is the shift from passive systems to active systems. For a long time, AI has primarily existed as something reactive. You give it an input, it gives you an output. You ask a question, it answers. You provide data, it analyzes. This paradigm is powerful, but it is fundamentally limited because the intelligence is not acting on its own initiative. It is waiting. Autonomous AI agents changed this paradigm completely by introducing systems that can plan, act, observe, and adapt over time with minimal human intervention. To understand autonomous AI agents, it is useful to think of them not as tools, but as entities operating within an environment. An autonomous agent has goals, access to resources, the ability to make decisions, and the capability to execute actions. Instead of responding to a single prompt, it operates in a loop. It receives an objective, breaks it down into tasks, executes those tasks, evaluates the results, and iterates. This loop is what transforms a simple language model into something that resembles a digital worker. At the core of an autonomous agent is a combination of several components working together. First, there is a reasoning engine, typically powered by a large language model, which interprets goals and generates plans. Then there is memory, which allows the agent to store and recall information across steps. This can include short-term memory for the current task and long-term memory for accumulated knowledge. Next, there are tools or action interfaces, which allow the agent to interact with external systems such as APIs, databases, or software environments. Finally, there is a control loop that orchestrates the entire process, ensuring that the agent continuously evaluates progress and adjusts its strategy. One of the most important aspects of autonomous agents is their ability to decompose complex problems. Instead of trying to solve everything in a single step, the agent breaks down a high-level goal into smaller, manageable tasks. For example, if the goal is to launch a marketing campaign, the agent might first research the target audience, then analyze competitors, generate content ideas, create drafts, schedule posts, and monitor performance. Each of these steps can be further broken down, executed, and refined. This hierarchical planning capability is what enables agents to handle tasks that would otherwise require human coordination. Another key characteristic is persistence. Traditional AI systems are stateless or session-based, meaning they do not maintain continuity beyond a single interaction. Autonomous agents, on the other hand, persist over time. They can revisit tasks, track progress, and maintain context across multiple steps or even days. This persistence is essential for real-world applications where tasks are not completed instantly but require ongoing effort and adaptation. Memory plays a crucial role in enabling this persistence. Without memory, an agent would repeat the same mistakes or lose track of its progress. Memory systems can be implemented in various ways, including vector databases for semantic recall, structured logs for action history, and knowledge graphs for relationships between entities. The challenge is not just storing information, but retrieving the right information at the right time. Efficient memory retrieval mechanisms are critical for maintaining coherence and effectiveness in long-running tasks. Tool use is another defining feature of autonomous agents. A language model by itself can generate text, but it cannot directly interact with the world. By integrating tools, the agent gains the ability to perform actions such as sending emails, querying databases, executing code, or interacting with web services. Each tool expands the agent's capabilities and allows it to operate in more complex environments. The design of these tools and the interfaces between the agent and the tools is a major area of engineering effort. The control loop is where everything comes together. In a typical agent loop, the system starts by interpreting the goal. It then generates a plan, selects an action, executes it, observes the result, and updates its internal state. This cycle repeats until the goal is achieved or a stopping condition is met. The quality of the control loop determines how effectively the agent can adapt to new information and handle unexpected situations. Designing robust control loops is one of the biggest challenges in building reliable autonomous systems. Now, when we move from theory to practical applications, the impact becomes very clear. One of the most prominent use cases is the concept of an AI project manager. Imagine a system that can take a high-level objective such as develop and launch a new feature and manage the entire process. It can break down the work into tasks, assign priorities, track progress, communicate with team members, and adjust timelines based on delays or new requirements. This does not mean replacing human project managers, but augmenting them with a system that can handle routine coordination and data-driven decision-making. In customer support, autonomous agents are already transforming how organizations interact with users. Instead of simple chatbots that answer predefined questions, modern agents can handle entire workflows. They can understand complex user requests, retrieve relevant information, execute actions such as processing refunds or updating accounts, and follow up if necessary. They can also learn from past interactions, improving their performance over time. This leads to faster response times, lower operational costs, and more consistent user experiences. Self-optimizing business processes represent another major application area. Many business operations involve repetitive tasks, decision-making based on data, and coordination between multiple systems. Autonomous agents can monitor these processes, identify inefficiencies, and take corrective actions. For example, in supply chain management, an agent can track inventory levels, predict demand, adjust orders, and coordinate with suppliers. In finance, it can analyze transactions, detect anomalies, and generate reports. The key idea is that the system is not just executing predefined rules, but continuously improving its behavior based on feedback. However, building autonomous agents is not just about combining components. It requires careful consideration of reliability, safety, and alignment. One of the main challenges is ensuring that the agent's actions remain aligned with the intended goals. Because the agent operates independently, there is a risk that it might pursue suboptimal strategies or misinterpret instructions. This is known as the alignment problem, and it becomes more critical as agents gain more autonomy. Error handling is another important aspect. In real-world environments, things do not always go as planned. APIs fail, data is incomplete, and unexpected situations arise. An effective agent must be able to detect errors, recover from failures, and adapt its strategy. This requires robust monitoring, fallback mechanisms, and sometimes human-in-the-loop intervention. Designing systems that can gracefully handle uncertainty is essential for practical deployment. Evaluation of autonomous agents is also more complex than traditional AI systems. Instead of measuring accuracy on a static dataset, we need to evaluate performance over sequences of actions and long-term outcomes. Metrics might include task completion rate, efficiency, robustness, and user satisfaction. Developing standardized benchmarks for autonomous agents is an ongoing area of research. Another dimension to consider is scalability. As the number of agents and tasks increases, managing interactions between them becomes more challenging. In some scenarios, multiple agents may need to collaborate, share information, and coordinate actions. This leads to the concept of multi-agent systems, where a group of agents works together to achieve a common goal. Coordination mechanisms, communication protocols, and conflict resolution strategies become important in such systems. Security and privacy are also critical concerns. Autonomous agents often have access to sensitive data and the ability to perform actions that can have real-world consequences. Ensuring that these systems operate securely, respect user privacy, and comply with regulations is essential. This includes implementing access controls, auditing mechanisms, and safeguards against malicious use. From an architectural perspective, building autonomous agents involves integrating several layers. At the bottom, there is the infrastructure layer, which includes compute resources, storage, and networking. Above that, there is the model layer, where the language models and other AI components reside. Then there is the orchestration layer, which manages the control loop, task decomposition, and tool integration. Finally, there is the application layer, where specific use cases are implemented. Each layer must be designed with scalability, reliability, and maintainability in mind. One of the most interesting aspects of autonomous agents is how they change the way we think about software. Traditionally, software is deterministic and explicitly programmed. With agents, we move towards systems that are partially learned, adaptive, and capable of reasoning. This introduces a new paradigm where developers are not just writing code, but designing behaviors and constraints within which the agent operates. Prompt design, tool selection, and control logic become as important as traditional programming constructs. There is also a shift in how humans interact with these systems. Instead of issuing detailed instructions, users provide high-level goals. The agent takes responsibility for figuring out how to achieve those goals. This requires trust, because the user is delegating control. Building that trust involves transparency, explainability, and consistent performance. Users need to understand what the agent is doing, why it is doing it, and how to intervene if necessary. Looking forward, the role of autonomous agents is likely to expand significantly. As models become more capable and integration with external systems improves, agents will be able to handle increasingly complex tasks. We may see entire workflows managed by networks of agents, each specializing in a particular function. For example, in a software development pipeline, one agent could handle requirements analysis, another could generate code, another could perform testing, and another could manage deployment. These agents would communicate and coordinate, creating a highly automated and adaptive system. At the same time, human oversight will remain important. Autonomous does not mean uncontrolled. The most effective systems will be those that combine the strengths of AI and human intelligence. AI can handle scale, speed, and data-driven decision-making, while humans provide judgment, creativity, and ethical considerations. Designing systems that leverage both is a key challenge and opportunity. In conclusion, autonomous AI agents represent a fundamental shift in how we build and use artificial intelligence. By moving beyond simple input-output interactions to systems that can plan, act, and adapt over time, we unlock new levels of capability and efficiency. From AI project managers to advanced customer support systems and self-optimizing business processes, the applications are vast and transformative. However, realizing this potential requires careful engineering, robust architectures, and a deep understanding of the challenges involved. As we continue to develop these systems, the focus will not only be on what they can do, but on how they do it, and how we ensure they operate in ways that are reliable, safe, and aligned with human goals.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.